Hello and welcome to this session of Introduction to Autonomous Systems. In the last segment, if you recall, we talked about basic concept of search, which is the first step in the direction of trying to find a conclusion or an inference which then can lead to the desired action. Let us first look at some of the basic techniques, and we start off with the blind or the uninformed search technique. So, let us begin. Blind or uninformed search technique actually has a very big canvas. There are large class of search techniques that come under this category. In fact, many of us, when we misplace items, generally go through this strategy of trying to search everywhere till we find it. So, blind search strategies are essentially of that type. Of course, there are still minor differences between their impact and their overall efficiencies. So, we will look at all of them which are pertinent to the kind of problem that we are intending to solve. So, this has actually resulted in 4 to 5 options as follows. First, we will look at the breadth first, then we will look at the uniform cost, we will look at the depth first, depth limited option, iterative deepening depth first, and bidirectional. These are the basic blind search techniques where you do not have any problem specific information and you just start the process at whatever the starting point which is specified and then continue the process until you find the goal or the solution. The breadth first technique starts by expanding the root node or the starting point, followed by expansion of successors of root node recursively for a given depth level before the next level is taken up, which essentially means that we go conceptually at least horizontally first, finish all the nodes horizontally before going down vertically, and that is how the name has been attached to the technique, saying breadth first. Essentially, we are looking at this problem from a two-dimensional tree search perspective. However, this is also typically what we call a graph search method, in which the shallowest unexpanded node is chosen first, as shown in the figure below. So, let us look at it. Now, as we can see, the tree A, or starting with node A, is the parent node or what we call the root node, and then let us say we have successors like B, C, D, E, F, G and so on. Now, if you go from left to the right of the figure, you will note that initially the first root node is expanded A, whose successors are B and C, and our pointer now shifts to B, because there are no more nodes at the same level as A. So, you go to the next depth level and look at B. Now, when you expand B, you generate its successors D and E, but then you first move over to C, that is where you see in the third graph the pointer at C, you expand those and you get F and G. Once you have exhausted the nodes at the second level, Then you shift the pointer to the third level, and again you conceptually move from left to right. Like for example, you will go to D and E, then you will go to F and G, like that. It will continue the process depending upon the breadth level and the depth level. The process will continue until you have found the solution. Now, there is another attribute which we need to look at. Every time we expand a node or take a step, there is going to be a cost attached to it. It could be in terms of an effort, it could be in terms of time taken. Now, it has been found that if all the steps have equal cost, then the breadth first process that we have looked at gives an optimal solution, but in case the various steps have different costs, then another strategy of what is called uniform cost search helps in arriving at an optimal solution. What it essentially means is that if you have differential costs, then by taking those steps which have the same in a tree actually helps in arriving at an optimal solution, which means it is almost like saying that shortest path to destination. So, at every stage you look for the path which has same cost as the previous one. So, in this algorithm actually what happens is that you take, instead of shallowest node, it expands the node with least cost. So, I just want to show you a small segment of a schematic in which the task is to go from a location Sibiu to a location Bucharest. This is a sample of a map of Romania. Now, as we can see, the lines have numbers written on it which are indicator of the cost. In this case, it essentially is the straight line distance between these two locations. And now, as you can see, if you start from Sibiu, then you see that there are two successors, Făgăraș and Râmnicu, whereas the cost of Făgăraș is 99, of Râmnicu is 80, and obviously you will choose that path. After that, you will obviously you have only one successor 97, so you will end up going in that direction, and then finally you go to the last one which has the cost of 100. So, if you add all these costs, you will find that this cost is lower than the cost of the other path. You can do a simple arithmetic to confirm this idea. So, now you realize that by choosing the paths which have least cost among all the successors, you actually can end up with an optimal solution. So, you do not really go to the breadth first, you just look for the least cost solution. As against these two, that is breadth first and the uniform cost, we have now an alternative in the form of depth first strategy. In this, the deepest unexpanded node is taken up first, as shown in the figure alongside. So, again we have a tree. Now, instead of D, E, F, G, where it stopped in the previous example in the breadth first, now we have one more level of H, I, J, K, L, M, N, O, and we start the same process. A is the only node at its level. So, you come to the next depth level, that is B and C, you expand B, but instead of going to C, which is what we had done in the context of breadth first, you start expanding B further, which is D and E, and then you go down to D. Again, once you have expanded the B to D and E, you go to the level D and you again further go down and expand H and I. Once you have done this, then of course you start looking at different. So, you will first look at, so basically you are not going to see at all. So, now what you will do is that let us assume that beyond H and I there are no further successors. So, the process goes up to D, it takes up next level, that is E, and it expands E to J and K. After that only it goes one level up, then it takes up C, and then it starts expanding the other branch. So, you realize that this is a slightly different way of searching for the solution. Now, the fact that we do not know anything about the problem and also the location of its solution, it is possible that either breadth first or the depth first could provide a quicker solution, one of them or both of them, depending upon the scenario. Now, in this case it so happened that M is the goal node, and if we had done the breadth first, you would realize that we would have expanded all the nodes at the other level as well, like E, F and G, before coming down to the level M. But in the present case, because we were at already a depth level, it was quicker for us to identify the goal node M. But there is a problem. The problem is that if you have a problem which is infinite dimensional, then this process is never complete, because it cannot find the solution even if it exists. For example, if the solution was existing somewhere towards the breadth wise limit, it would take too much of time to reach that breadth level. So, this is the issue with the depth first search strategy. Of course, the drawback of this particular technique is somewhat mitigated by limiting the depth to which you will go. So, in this present case that we have seen, we go to the deepest level till there are no more successors. But in the depth limited search, we do not do that. What we do is that we upfront fix a depth level where we think the solution might lie, even though it is higher than the deepest level, and then we go only up to that depth level and then do the breadth wise search. So, now you realize that the choice of depth is going to be critical to avoid the same problem of incompleteness. But at the same time, if you have chosen a depth level which is not sufficient, you will never be able to find the solution until lot of time has been spent in finishing the breadth. So, there are problems, and it is found that such techniques generally work better if there is a priori knowledge. For example, if somebody says that the item that you lost was in a room, it becomes easier for you to limit your search domain and number of places that you want to search to find this. Instead of saying that it could be anywhere, it's like almost saying that you dropped keys somewhere and now you are looking for them. And if you were on the move outside, it could be anywhere on the road. So, you go and check all the destinations where you were But if suppose you were known that okay, last I saw the same item was when I was there and after that I have simply come home, then it becomes easier for you to just search that particular place. In between these two, that is the depth first and the depth limited search, there is an alternative called iterative deepening depth first. So, here what you do is you do not know the depth level that you should choose. So, you kind of vary the depth level successively. You start with one depth level, go and see if the solution is found, you reset it to the next depth level and then again do the search, and that will probably reveal what is the best depth level at which the solution is to be found. So, this essentially is in some way combination of the depth first and the breadth first technique. Of course, the issue is that this will require again more time. However, let us look at how this thing works out. So, now initially you set the limit to 0, which means you are not going to go anything beyond the starting or root node and check whether it is a solution or not. Then you reset the limit to 1 and then go to B, C and complete that tree horizontally before you change the limit to 2, go back and complete the solution for the depth level of 2, then you put the depth level equal to 3 and you keep doing this until you find the solution. The uninformed blind search strategy, the last strategy, is a kind of a common sense based intuitive strategy that says that if you know the starting node and if you know the destination node, you are looking for a path to reach the destination, and that is the whole search problem is all about. Then can we not do a thing where we start or attack the problem from both ends, that we start search from the start node and we also start back search, which means from the start node we have a forward search, from the goal node we have the backward search. So, you start creating two search domains. Now, the basic premise is that b to the power d by 2 plus b to the power d by 2, this number is always less than b to the power d. This you can numerically verify. This is the basic premise for a given problem. So, now the goal test is replaced by the condition of two searches meeting in the middle. So, the way it works is something like this, that you have a start node and then you have number of branches going out towards the goal, and then you have a goal node from which number of branches are coming towards the start node. Now, as you can see, at some point there will be one branch in both of them which will come together, and once that happens you can stop the search, because now you know that from start node to that point how to go and from that point to goal how to go. So, you already have found the goal node path. So, this is the way it works. So, how do we kind of benchmark these or kind of evaluate the quality of these search techniques? So, there are general broad guidelines. So, there are about 4 criterion which have been used to trade one against another. So, we say these criterion are complete, time, space and optimal. So, whether it is a complete technique, whether it takes what amount of time, it takes what amount of space, and is it optimal. So, if you look at breadth first, it is complete, it is also optimal, and it takes time of the order of b to the power d, and it also takes the space of the order of b to the power d. If you look at the uniform cost, then again it is complete and it is optimal. Of course, the time is different. We will discuss those parameters which are there. Depth first, it is not complete, we have already seen it. It is also not optimal, and the time it takes is b to the power m as well as the space which is b to the power m, bm, b into m. Now, depth limited also is not complete and not optimal. Iterative deepening, because it is combining breadth first and the depth first, becomes complete as well as optimal, and of course, it is a better way of doing it. And bidirectional of course has the benefit that it also has less space, less time, and it is complete. Some of these superscripts are the riders that we need to understand. So, subscript caveats are: A is complete if B is finite, B complete if step costs are greater than epsilon for epsilon greater than 0, some numerical threshold. C is optimal if all step costs are identical. D, both directions use breadth first search. Then the D has this solution. So, to conclude this part, the blind search is somewhat similar to model checking algorithm, in which one searches the whole domain in order to find the solution. You remember this when we were talking about our logical strategies, and there we said that entailment has to be checked before you can say that this statement is true in checking all the models. This is almost like checking all the models before saying whether the entailment is there or not there. And you need to realize that such strategies with applicable enhancements are likely to become intractable with increase in size of the problem. What it means is that even if you choose any one of those options like uniform cost or iterative deepening of depth, or if you look at the bidirectional, at some point they will become intractable, which means the solution exists, but you can't find it. So, with that we come to the end of this part, and we will continue the discussion in the subsequent session. So, bye for now and see you in the next session.